So this is section 10.3, the gas laws. Gases are described by 4 different variables: pressure, volume, temperature, and number of moles of gas. These 4 variables all have relationships with one another, and they're named for famous scientists. The relationship between volume and pressure is called Boyle's law. Between temperature and volume is called Charles' law. Between temperature and pressure is known as Gay-Lussac's law. And between volume and number of moles of gas is known as Avogadro's law. We're going to take a deeper look at each one of these 4 relationships right here, and we'll look at how mathematically they change when the other variables are held constant. So I'm going to scoot this over here, we'll move this table over here, and then let's look first at Boyle's law. So you don't need to know the name of the law, but you need to know the relationship. And if you take and hold temperature and number of moles of gas constant, volume and pressure are inversely related to one another. Volume times pressure will give you a constant. If you graph volume versus pressure, once again keeping temperature and number of moles of gas constant, you'll get an inverse relationship graph. I like to think of it this way. The volume and pressure are known as the vice president law. If the president goes down, well, the vice goes up. And so it's an inverse relationship between those two. Volume is inversely proportional to pressure. That's the first one to know. The second one is the relationship between volume and temperature, known as Charles' law. Volume and temperature are directly related to one another. If you graph volume versus temperature while you're holding pressure and number of moles of gas constant, you'll get a straight line going up and to the right. If you increase the temperature, you increase the volume, or if you increase the volume, you increase the temperature. It is a direct relationship. I like to think of it like this. There used to be television sets in the world, TVs in the world, that had little things on the top. These were called antennae. If one antenna goes up, the other one goes up. So there's your television relationship. So the vice president relationship, the television relationship. 2 of the 4 relationships we need to know. All right, the next one is a relationship between temperature and pressure. Temperature and pressure are a direct relationship with one another. Temperature and pressure, when volume and number of moles of gas are held constant, will both increase with each other. If you increase the temperature, you increase the pressure. If you increase the pressure, you increase the temperature. And if you graph the two, once again, holding volume and number of moles of gas constant, you would see a direct relationship. I like to think of this one as the toilet paper relationship. If you flush the toilet, the paper goes down. So there's your TP direct relationship. So vice president, television, toilet paper, 3 relationships you can easily remember. The last one is number of moles of gas and volume. This is known as Avogadro's law, and Avogadro's law is also a direct relationship. If you increase the number of moles of gas while holding pressure and temperature constant, you will increase the volume of that gas's container. There's a direct relationship, so if one goes up, the other one goes up. This one doesn't really have a neat way to remember it other than it's NV, and it's also a direct relationship. And you can see from these 4, only one is an inverse relationship. The other ones are all direct, 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 meaning one thing goes up, the other thing goes up. So those are the 4 relationships that you need to know. Let's summarize them all in one little handy piece, and then looking at the summary, let's see if we can answer a couple of questions. So here's the vice president relationship, volume and pressure. One goes up, the other one goes down, an inverse relationship. The television relationship, one goes up, the other one goes up, a direct relationship. The toilet paper relationship, one goes down, the other one goes down. And then our NV relationship, which is Avogadro's law. One goes up, the other one goes up, or one goes down, the other one goes down. So notice 3 are directly proportional to one another as long as the other variables are held constant, and one is inverse. So here's a question for you. Let's see if we can use this summary to help ask it. We've got a container of gas, sealed shut, 10-liter container. It's at 1 atmosphere of pressure and 273 Kelvin, which happens to be 0 degrees Celsius. And we have 1 mole of the gas inside of here. So we have all the variables. We have volume, we have pressure, we have temperature, and we have number of moles of gas. So using this qualitatively, what would happen if we heated this gas? So we put a flame underneath here and we heated it up. What would happen to the volume? Well, if it's a real sealed container, it would not change, right? Because the container can't change if it's a rigid, held together container. What would happen to the temperature? Well, the temperature of gas would go up. The molecules would move faster and our temperature would increase. What would happen to the pressure? Well, if the molecules start to move faster and the temperature goes up, what happens to the pressure? Well, they're directly related to one another, and so if temperature goes up, pressure should go up inside of there. There's more collisions of the molecules. What would happen to the number of moles of gas? Well, they should remain the same, right? Because we have a sealed container of 10 liters, and we didn't allow any gas in or any gas out. How about if we cooled it? Well, the opposite would happen to some of the things. The volume would remain the same, of course. The number of moles of gas would remain the same because we didn't open the container or change its size. And then the temperature, of course, would go down, the molecules would slow down, and the pressure would also go down. Last one, what happens if we compressed it or crushed it, like actually uniformly squished the container? Well, the volume would go down, obviously, because we're compressing or crushing it. So assuming it doesn't leak, the number of moles of gas would remain the same because we didn't allow any gas in or out. The temperature, well, what happens? If the volume goes down, what happens to the temperature? Well, if the volume goes down, the temperature would go down. Is that true? As long as we have the pressure remaining the same. But here's the trick. If we squish this container and our volume goes down, our pressure would go up. And so the pressure would increase dramatically as we squash this, and if we increase the pressure, we would increase the temperature inside of here. All right, so those virtual types of questions you should be able to ask yourself, and you should have a qualitative answer to them as far as like the changes that go. And then in this next video, we'll look quantitatively, mathematically, at all of these changes and give numerical values and put them into our calculator.